This example is about automating a suite of plant model acceptance tests as proposed in IEEE P2800.2 subgroup 3 in various parts of clause 7. And this is from D0.5 from the summer of 2023. So there may be changes between now and the final version. It's important to know that they want the test to be done at a short circuit ratio of 2.5, and so that raises the question of where the point of connection should be defined. So we normally think of it as the transmission bus at the 230 kV in this case, but in this case, and most plants, they're going to have significant reactive impedances inside the plant. So we have the inverter step-up transformers, we have possibly a collector feeder equivalent, and we also have the park interconnection transformer. So we have two different 100 megawatt IBR examples, one solar, one wind. They have different impedance elements. So these add up to significant inductive reactance. If we want a short circuit ratio of 250 MVA, then we want to see on a 230 kV base 211.6 ohms. Inside the plant, we already have 74 ohms to 100 ohms. And that means that at the inverter terminals, if we had a very strong grid, the highest short circuit MVA and the highest short circuit ratios we could get are about 7 in the case of the solar plant and about 5 in the case of the wind plant. If we try to use higher grid impedances, if we try and get a short circuit ratio 2.5 here at the point of connection, it is hard from a steady state transfer perspective to get full 100 megawatt export out of the plant. So we end up, instead of 211.6 ohms, we ran these tests at J137 or J111. So we're getting actually the short circuit ratio we want to get is here at the voltage source converter terminals. And so we may revisit this test procedure, and we may issue some comments to P2800.2 subgroup 3 and maybe clarify what the test procedure should be in terms of the point of connection and the short circuit ratio. So there are a number of tests to show on subsequent slides, but the models have been modified so that we can do some of the control ramp reference tests for control functionality. So the plants will have a set point for P, Q, power factor, or voltage, but you also want to have some step change inputs, and those are the ones in blue. We also have some changes in grid voltage characteristics. So it's a 230 kV source. It can be a strong or weak source. But we may want to change the voltage source magnitude, the frequency, or the phase angle to do different parts of the test. So if we want to simulate an overvoltage, the most convenient way to do that is just to increase the grid voltage magnitude. So those are control inputs for the grid voltage source. There is also an interesting test. It's an informative test, informational test on short circuit ramping ratio, and I have a slide to show that later. But in order to set that up, we have switchable grid impedances here, where we can go between 7 or 8 grid impedance levels to go from, say, 0 or near 0 grid impedance all the way up to the 74 or the 100 ohms, depending on which solar plant we're looking at. And these grid impedances change at 5-second intervals, and they change during a voltage fault. So it's a non-physical test, but it's informational on how well the model and the controls perform. Okay. One set of tests that we can do with the just the faults or just the control reference inputs are the model initialization, the undervoltage, and the control step tests. So there's some flat start model initialization tests where we start from 0. So we're not initializing from a steady state load flow, but from 0, like a black start of the plant. And the model should initialize from 0 smoothly and then remain stable at the desired operating condition for 10 seconds. And remember, this is supposed to be at a short circuit ratio of 2.5. So there's 7 variations we can do. 7 variations of control. So we have the voltage control mode at 1 per unit. We have leading and lagging reactive power, fixed Q mode. And we also have power factor control mode at 0.95 and minus 0.95. We do this at two different power levels. You can think of this as Pmax, the inverter continuous current rating, and also a Pmin. In our examples, in one case Pmin is 0, in the other case it's 0.04 per unit, but 2 times 7 is 14, so 14 variations of the model initialization test. We have a second, and so in the file naming scheme, we're limited to 8 characters for ComTrade files, so I picked a 2-character mnemonic FS for flat start. That's a sequence of model initialization tests. We have 15 undervoltage ride-through tests. The fault duration is going to be 0.16 seconds, so it's not the 0.3 seconds we did in the previous example of fault automation. These are all done at inverter continuous rating, kind of like Pmax. And we do different variations. We do 3 fixed Q values of 0.3287, 0 or minus 0.3287. And we do 5 different fault types. One isn't really a fault. It's a 3-phase sag to 50% voltage. And so we simulate that with a inductive fault on the point of connection, but what that really represents is a 3-phase fault somewhere deep in the power system where the IBR is connected, it's going to see 50% voltage. We also have bolted faults of the 4 basic types: 3-phase to ground, single-phase to ground, and 2-phase to ground, and then phase to phase. Depending on the IBR characteristics and the short circuit ratio, sometimes you have to be careful with these fixed key values of 0.3287 or minus 0.3287. That could cause a steady state voltage rise or drop that may trigger some of the undervoltage or overvoltage protection, depending how long those voltage deviations last. The third set of tests that can be done this way is the 4 control reference change tests that are plotted below. So we have a delta VREF. It starts at 1 per unit, and then we add 0.5, or we subtract 0.5, and this is a 50-second test. So we're giving 10 seconds of operating region where the plant is supposed to stabilize these different control reference settings. We have an active power test that lasts 40 seconds, so it is 1 second at 1 per unit power, and then we drop down to 50% power for another 10 seconds. We go to 4% power for the third 10-second period, and then go back up to rated power 1 per unit. There's a reactive power test where we are injecting reactive power at 0.3287 per unit. And then, so by the way, that's a power factor of 0.95. So that lasts for 10 seconds. We recover to 0 Q, and then we go to minus 0.3287, which means it is absorbing reactive power, even though it's generating active power at the same time. The equivalent in power factor test is to inject reactive power. We drop the power factor from 1 to 0.95, and then to absorb reactive power, it's going to a power factor of minus 0.95 between 30 and 40 seconds. This sequence of tests is done by modifying the grid voltage source. So the overvoltage tests, we need to create a 1.2 per unit voltage that's going to last, for 1 second, and so the plant should ride through that. If it's at 1.21 per unit, the plant is allowed to trip. So there may be a little bit of numerical precision and voltage rise and voltage drop to worry about here, but at 1.2 per unit, we want the plant to ride through, and we do this at maximum power output, ICR, and then 3 fixed Q values. The next set of 4 tests that we do are the frequency ride through, and we have a couple of values to test that. We stabilize at 60 Hertz for the first 5 seconds, and then for the next 20 seconds, we're either going to add 1.8 Hertz to the source frequency, or we're going to decrease it by 3 Hertz, drop to 57. The IBR should ride through either one of those. We're doing power at ICR and Pmin, and in both of those, we're doing fixed Q equals 0. So unity power factor for frequency ride-through test. The last set that we do with the source changes is angle ride-through, or sometimes it's called phase angle jump. We again do that at P equals ICR, P equals P min, and then fixed Q equals 0. And we can do a positive or negative jump of 25 degrees between 10 and 30 seconds of the simulation. So this is going to disturb the phase lock loop operation, but it should recover. And so the IBR should not trip or anything. It should resynchronize to the new phase angle of the source voltage.